Thank you very much, and thank you everybody for being here today. So yeah, my name is Francesco Peverelli, and I'm a third-year PhD candidate here at Politecnico of Milan. So my main research interests revolve around domain-specific reconfigurable hardware, and in particular on instruments and ways to make it easier to design and prototype reconfigurable hardware, in particular when you're dealing with irregular and control-driven workloads. So, as we all know, we have an ever-increasing demand for more performance and the ability to process more data. And recent technological limitations have made clear that classical fundamental architectures are insufficient to meet this demand. And therefore, we push for research that goes into the direction of exploring different architectural models. So one of these architectural models we can explore are spatial architectures, where the main idea is that we have processing elements and memory elements which are spatially distributed across our chip, and then we have different interconnections which are basically tailored to the specific application that we want to execute. So the question then becomes, how do we keep the productivity and efficiency of making these domain-specific designs, and also how do we explore this design by keeping in mind that if we have irregular and data-driven workloads, we need a good way to prototype these architectures and make sure that they actually fit the data that we want to then process. So what SATL is, which is one of the works that I've been doing during my PhD, is a framework that is a collection of building blocks to create these spatial architectures that focuses on three main pillars. So on one hand, we want to be able to specialize the hardware components so that we can obtain the maximum performance. On the other hand, we want to keep modularity as much as possible to facilitate hardware reuse. And again, we also want to keep an eye on automation because we want to basically increase the productivity and decrease the design time for these architectures. Okay, so how does SATL achieve this? Well, it's a Chisel library. So Chisel is a hardware construction language, which then outputs Verilog. And basically what we've done is create a collection of building blocks which allow you to instantiate spatial architectures by taking the, say, templates for different architectural configuration and specializing them according to your needs. So the user will take some standardized components and then extend them to create a specific architecture. In addition, SATL also provides different prototyping flows to verify the architecture. In particular, we have two main flows. One is what we call a full SoC prototyping flow. So this allows you to integrate the SAT accelerator within a RISC-V-based system on chip, provided by the open source Shipyard framework. And the other flow instead, if you want to build an FPGA accelerator based on your spatial architecture, allows you to integrate with the Zynq UltraScale Plus MPSoC. So today I'll just, for the sake of brevity, talk about a case study we have done in the second flow, so the FPGA acceleration flow. And in particular, we have looked at decision tree inference. So this is a classical machine learning problem where you want to train a bunch of decision trees, so a random forest, to then basically do some inference on some sample data and perform a classification task. So the control-driven part of the workload, of course, is that for each sample, you want to traverse all the trees to figure out the classification class for each of them, and then perform a majority voting at the end to obtain the classification output. So we have created a SATL-based accelerator, which is the one you see on the bottom left. And basically, this is a memory-centric architecture where before we train the random forest with an architecture-aware training phase. And then we basically utilize a specific data layout to fit our trees into different VRAMs. And what happens is that the samples flow in a data flow manner in a streaming fashion through the processing elements of the architecture. And at each step, we evaluate one level of each tree. And then to evaluate multiple trees, basically the sample loops back around and again, evaluates the different trees that are stored into the local memories. So what we did is compare the performance of our SATL-based accelerator with a state-of-the-art accelerator for the same task that was based on a previous Vitis high-level synthesis design. And here in the table, you can see a few different parameters. So on the x-axis, you have the number of trees that you can fit on the architecture. And on the y-axis, you have the depth, the maximum depth of the trees for these models. So what you can see is in the upper table, you have the latency of our solution compared to the Vitis HLS1. We can see that we achieve up to 3.72 times better latency, and this is due to on one side, better optimization of the computation pipeline, and on the other side, better operating frequency that we achieve with our design. On the lower table, you can also see the resource saving in terms of the critical resource for the architecture, which were lookup tables in this case. And you can see that we can save up to 42%, we use up to 42% less lookup tables than the original HLS design. Moreover, where you see SATL in different points of the table, it means that we can, for example, synthesize that configuration, whereas the previous architecture could not do it because it runs out of hardware resources available on the UltraScale Plus board. So in conclusion, then we also compared our implementation to an implementation which was handwritten chisel code without the SAT library to evaluate basically the impact of using the library as opposed to handwriting all the code. You can see that we save 40% in the number of lines of code, and in particular, we note that all this code is mainly comprised of interconnection logic and standardized components, which did not need to be basically handwritten if you had a support of an appropriate library. So this is all from my side. The framework is open source, so this is the GitHub if you want to explore, and thank you for the attention.